Okay, onto the device model. So, a significant new feature in the 2.6 Linux kernel is the addition of a unified device model. The device model provides a single mechanism for representing devices and describing their topology in the system. Such a system provides several benefits. First is the minimization of code duplication, a mechanism for providing common facilities such as reference counting, the capability to enumerate all the devices in the system, view their status, and see what bus they attach. The capability to generate a complete and valid tree of the entire device structure of the system, including all buses and interconnections. The capability to link devices to their drivers and vice versa. The capability to categorize devices by their class, such as input device, without the need to understand the physical device topology. The capability to walk the tree of devices from the leaves up to the root, powering down devices in the correct order. The initial motivation for the device model was this final point: providing an accurate device tree to facilitate power management. To implement device-level power management in the kernel, you need to build a tree representing the device topology in the system. For example, what drive connects to what controller and what device connects to what bus. When powering down, the kernel must power down the lower leaf nodes of the tree before the higher nodes. Oh, that makes sense. Yes. Dependency is like a graph. For example, the kernel needs to turn off a USB mouse before it turns off the USB controller, and the kernel must power down the USB controller before the PCI bus. To do this accurately and efficiently for the entire system, the kernel needs a tree of devices. K-objects. At the heart of the device model is the K-object, or short for kernel object, which is represented by struct K-object and defined in Linux /kobject.h. The K-object is similar to the object class in object-oriented language such as C# or Java. It provides basic facilities such as reference counting, a name, and a parent pointer, enabling the creation of a hierarchy of objects. Without further ado, okay, here is the K-object struct. Again, it's probably linked lists, okay? What else do we have here? So we have some state that's being kept in unsigned ints. Then we have a name here. So he'll go over it right here, I bet. Yeah. So the name pointer points to the name of this K object. The parent pointer points to this K object's parent. In this manner, K objects build an object hierarchy in the kernel and enable the expression of the relationship between multiple objects. As you shall see, this is actually all that sysfs is, a user space file system representation of the K-object object hierarchy inside the kernel. The SD pointer points to a sysfs durant structure that represents this K-object in sysfs. Inside this structure is an inode structure representing the K-object in the sysfs file system. The kref structure provides reference counting. The ktype and kset structures describe and group K-objects. We look at them in the next two subsections. K-objects are usually embedded in other structures and are generally not interesting on their own. Instead, a more important structure, such as struct cdev, defined in Linux /cdev.h, has a K-obj member. Okay, so struct cdev has all these properties, K-object, so that's the one that we just went over. Yeah, another linked list, okay. So when K-objects are embedded inside other structures, the structures receive the standardized functions that a K-object provides. Most important, the structure's embedded K-object now enables the structure to become part of an object hierarchy. For example, the cdev structure is presentable in an object hierarchy via the parent pointer cdev kobj parent and cdev kobj.entry. Okay, K-types. K-objects are associated with a specific type called a K-type, short for kernel object type. K-types are represented by struct kobj type and defined in Linux /kobject.h. So again, here you go, the struct definition. K-types have the simple job of describing default behavior for a family of K-objects. Instead of each K-object defining its own behavior, the behavior is stored in a K-type, and K-objects of the same type point at the same K-type structure, thus sharing the same behavior. The release pointer points to the deconstructor called when a K-object reference count reaches 0. This function is responsible for freeing any memory associated with this K-object and otherwise cleaning it up. The sysfsops variable points to sysfsops structure. The structure describes the behavior of sysfs files on read and write. It's covered in more detail in the section adding files to sysfs. Finally, default attrs, default attrs, I guess, points to an array of attribute structures. These structures define the default attributes associated with this K-object. Attributes represent properties related to the given object. If this K-object is exported to sysfs, the attributes are exported as files. The last entry in the array must be null. K-sets. K-sets, or short for kernel object sets, are aggregate collections of K-objects. K-sets work as the base container class for a set of kernel objects, collecting related K-objects such as all block devices together in a single place. K-sets might sound similar to K-types and prompt the question, why have both? K-sets group related kernel objects together, whereas K-types enable kernel objects, functionally related or not, to share common operations. The distinction is kept to allow K-objects of identical K-types to be grouped into different K-sets. That is, there are only a handful of K-types, but many K-sets in the Linux kernel. The K-set pointer points at a K-object's associated K-set. K-sets are represented by the K-set structure, which is declared in linux/kobject.h. Okay. In this structure, list is a linked list of all K-objects in this K-set. List lock is a spin lock protecting this entry in the list. See Chapter 10, Kernel Synchronization Methods, for a discussion on spin locks. K-obj is a K-object representing the base class for the set, and uEventOps points to a structure that describes the hot plug behavior of K-objects in this K-set. uEvent, short for user events, is a mechanism for communicating with user space information about the hot plugging and hot removal of devices from a system. So the handful of structures thus far discussed is confusing, not because of their number, there are only 3, or the complexity, they are all fairly simple because they are all interrelated. So K-objects, K-types, and K-sets are all interrelated. In the world of K-objects, it is hard to discuss one structure without discussing the others. With the basics of each structure covered, however, you can develop a firm understanding of the relationships. The important key object is the K-object, represented by struct K-object. The K-object introduces basic object properties such as reference counting, parent-child relationship, and naming to the kernel data structures. The K-object structure provides these features in a standard unified way. K-objects in and of themselves are not particularly useful. Instead, K-objects are typically embedded in other data structures, giving those containing structures the features of the K-object. K-objects are associated with a specific K-type, which is represented by struct K-obj type and pointed at by the K-type variable inside the K-object. K-types define some default properties of related K-objects: destruction behavior, sysfs behavior, and default attributes. The K-type structure is not well named. Think of K-types not as grouping, but as a set of shared operations. Okay, so K-objects are then grouped into sets called K-sets, which are represented by struct K-set. K-sets provide 2 functions. First, their embedded K-object acts as a base class for a group of K-objects. Second, K-sets aggregate together related K-objects. In sysfs, K-objects are the individual directories in the file system. Related directories, say perhaps all subdirectories of a given directory, might be in the same K-set. So Figure 17.1 depicts the relationship between these data structures. Okay, so K sets and K objects. You have various K objects belong to that K set. Okay, sure. Managing and manipulating K objects. With the basic internals of K objects and friends behind you, it's time to look at the exported interfaces used for managing and manipulating K objects. Most of the time, driver writers do not have to deal with K objects directly. Instead, K objects are embedded in some class-specific structure, as you saw with the character device structure, and managed behind the scenes by the associated driver subsystem. Nonetheless, K objects are not intended to remain hidden and can seep through into driver code, or you might be hacking on the driver subsystem itself. The first step in using a K object is declaring and initializing it. K objects are initialized via the function kObjectInit, which is declared in linux/kobject.h. So void kObjectInit takes in a pointer to a struct kObject called kObj, and then it also takes in a pointer to a struct kObject type called kType. The function's first parameter is the object to initialize. Before calling this function, the kObject must be zeroed. This might normally happen during the initialization of the larger function in which the kObject is embedded. If not, a simple call to memset does the trick. Memset kObj 0 size of kObj, or a size of one of those pointers. So then it is saved to initialize parent and kset after zeroing. For example, struct kObj pointer kObj. So then we malloc basically the size of the pointer value, and then if that didn't go well, okay, no memory, otherwise memset set 0, then initialize. Okay, so this multi-step effort is handled automatically by kObjectCreate, which returns a newly allocated object. So pointer to a struct called kObjectCreate, so it's a function pointer that takes in void. Usage is simple. Okay, so given that we declare a pointer to a struct kObject, we can just call kObjectCreate without any arguments because it's not expecting any, and that does everything that we read up here. So yeah, so most uses of kObjects should favor kObjectCreate or a related helper function rather than directly manipulate the structure. Cool. Reference counts. One of the primary features provided by kObjects is a unified reference counting system. After initialization, the kObject's reference count is set to 1. So as long as the reference count is non-zero, the object continues to exist in memory and is said to be pinned. Any code that holds a reference to the object first elevates the reference count. When the code is finished with the object, the reference count is decremented. Bumping the reference count is called getting a reference to the object, and decrementing the reference count is called putting a reference to the object. When the reference count reaches 0, the object can be destroyed and any associated memory freed. Incrementing and decrementing reference counts. Incrementing the reference count is done via kObjectGet, declared in linux/kobject.h. So again, we declare this function pointer called kObjectGet that returns back a pointer to a struct called kObject. Okay, this function returns a pointer to the kObject or null on failure. Decrementing the reference count is done via kObjectPut, also declared in linux/kobject.h. So this is also another function pointer, but now it takes in a single argument that is a pointer to a kObject type. Or a struct kObject type. So if the provided kObject's reference count reaches 0, the release function pointed at by the ktype associated with the kObject is invoked, any associated memory is freed, and the object is no longer valid. Okay. Krefs. Internally, the kObject reference counting is provided by the kref structure, which is defined in linux/kref.h, struct kref atomic t ref count. Okay, So the lone member is an atomic variable used to hold the reference count. A structure is used simply to provide type checking. Before using a kref, you must initialize it via kref init, right? Okay, and as you can see, this function simply initializes the internal atomic T to 1. Consequently, krefs are pinned with a reference count of 1 as soon as they are initialized. This is the same behavior as k-objects. To obtain a reference to a kref, use kref get declared in linux/kref.h. Okay, so kref get, the implementation is here. So we increment the reference count. Okay, this function bumps the reference count. It has no return value. To drop a reference to a kref, use kref put declared in linux/kref.h. So here we go. This is probably dec, kref dec or something. Yeah, atomic dec in test. And drops the reference count by 1 and calls the provided release function if the count is now 0. Okay. As noted by the ominous warn on statement, the provided release function cannot simply be k-free, but must be a specialized function that accepts struct kref as its lone argument and has no return value. The function returns 0 unless we put the reference, unless the put reference was the last reference to the object, in which case it returns 1. Normally, callers of kref put are unconcerned with the return value. Rather than having the kernel code implement its own reference counting via atomic T types and simple get and put wrapper functions, developers are encouraged to use the kref type and its helpers to provide a common and known correct reference counting mechanism in the kernel. All these functions are defined in lib/kref.c and declared in linux/kref.h. Cool. All right, sysfs. Okay. The sysfs file system is an in-memory virtual file system that provides a view of the k-object hierarchy. It enables users to view the device topology of their system as a simple file system. Using attributes, k-objects can export files that enable kernel variables to read from and optionally written to. Although the intended purpose of the device model was initially to provide a device topology for power management reasons, an offshoot was sysfs. To facilitate debugging, the device model's developer decided to export the tree as a file system. This quickly proved quite useful, at first as a replacement for device-related files that previously found themselves in /proc, and later as a powerful view into the system's object hierarchy. Indeed, sysfs, originally called driverfs, predated k-objects. Eventually, sysfs made it clear that the new object model would be quite beneficial, and k-object was born. Today, every system with a 2.6 kernel has sysfs. Most systems mount it as /sys/sys. The magic behind sysfs is simply tying k-objects to directory entries via the d-entry member inside each k-object. Recall from chapter 12 that the d-entry structure represents directory entries. By linking k-objects to d-entries, k-objects trivially map to directories. Exporting the k-objects as a file system is now as easy as building a tree of the d-entries in memory. But wait, k-objects already form a tree, our beloved device model. With k-objects mapping to d-entries and the object hierarchy already forming an in-memory tree, sysfs became trivial. So figure 17.2 is a partial view of the sysfs file system mounted as /sys. Okay, so that's fairly easy. So you have block devices, and then you have all the block devices associated in here. Let's see if we can find something interesting that we're familiar with. Oh, here's a keyboard. I think that's i8042. You also have, I guess, the disk file system. What else? Fuse, which is files. I think it's a file system in user space. Yeah. So the root of the sysfs contains at least 10 directories: block, bus, class, dev, devices, firmware, fs, kernel, module, and power. The block directory contains one directory for each of the registered block devices on the system. Each of those directories in turn contains any partitions on the block device. The bus directory provides a view of the system buses. The class directory contains a view of the devices on the system organized by high-level function. The dev directory is a view of registered device nodes. The devices directory is a view of the device topology of the system. It maps directly to the hierarchy of device structures inside the kernel. The firmware directory contains a system-specific tree of low-level subsystems such as ACPI, EDD, EFI, and so on. The FS directory contains a view of registered file systems. The kernel directory contains kernel configuration options and status information, while the modules directory contains a view of the system's loaded modules. The power directory contains system-wide power management data. Not all systems have all directories, and yet other systems have directories not mentioned here. The most important directory is devices, which exports the device model to the world. The directory structure is the actual device topology of the system. Much of the data in other directories is simply alternative organizations of the data in the devices directory. For example, sysclassnet organizes devices by the high-level concept of registered network interfaces. Inside this directory might be the subdirectory eth0, which contains a symlink device back to the actual device directory in devices. Take a look at sys on a Linux system that you have access to. Such an accurate view into the system's device is neat. And seeing the interconnection between the high-level concepts in class versus the low-level physical devices in devices and the actual drivers in buses is informative. The whole experience is even more rewarding when you realize that this data is provided for free as a side effect of the kernel maintaining a device hierarchy, and that this is the representation of the system as maintained inside the kernel. So this gives a lot of information and allows us to do even create tools that can inspect temperature of the system or control speed and things like that for various devices. So adding and removing k-objects from sysfs. Initialized k-objects are not automatically exported to sysfs. To represent a k-object in sysfs, you have to use k-object add. So we use this function here, k-object add, takes in a pointer to a struct k-object, also takes in a pointer to a struct k-object with a parent, and the formatted string, I guess. A given k-object's location in sysfs depends on the k-object's location in the object hierarchy. If the k-object's parent pointer is set, the k-object maps to a subdirectory in sysfs inside its parent. If the parent pointer is not set, the k-object maps to a subdirectory inside. Inside kset k-obj. If neither the parent nor the kset fields are in the given k-object, the k-object is assumed to have no parent and maps to the root level directory in sysfs. In most use cases, one or both of the parent and kset should be set appropriately before k-object add is called. Regardless, the name of the directory representing the k-object in sysfs is given by fmt, which accepts a printf style format string. The helper function k-object create and add combines the work of k-object create and k-object add into one function. So k-object create and add is this function. So note that k-object create and add receives the name of the k-object's directory as a direct pointer name, while k-object add uses printf style formatting. Removing a k-object sysfs representation is done via k-object del, which is k-object del here, takes in that k-object pointer. And all of these functions are defined in libkobject.c and declared in Linux kobject.h. Cool. So adding files to sysfs. K-objects map to directories, and the complete object hierarchy maps nicely to the complete sysfs directory structure. But what about files? Sysfs is nothing but a pretty tree without files to provide the actual data. Default attributes. A default set of files is provided via the ktype field in kobjects and ksets. Consequently, all kobjects of the same type have the same default set of files populating their sysfs directories. The kobject type structure contains a member default attributes that is an array of attribute structures. Attributes map kernel data to files in sysfs. The attribute structure is defined in linux/sysfs.h. Okay. The name member provides the name of this attribute, okay? And this will be the file name of the resulting file in sysfs. The owner member points to a module structure representing the owning module, if any. If a module does not own this attribute, this field is null. The mode member is a mode T type that specifies the permissions for the file in sysfs. Read-only attributes probably want to set this to SIRUGO if they are world readable, and SIRSUSR, IRUSR if they are only owner readable. Writable attributes probably want to set mode to SIRUGO or SIWUSR. All files and directories in sysfs are owned by UID 0 and GID 0. Although default ATTRS lists the default attributes, sysfs ops describes how to use them. The sysfs ops member is a pointer to a structure of the same name, which is defined in linux/sysfs.h. Okay, so show, store, function pointers, returns size t. Okay, the show method is invoked when the sysfs entry is read from user space. It must copy the value of the attribute given by ATTR into the buffer provided by buffer. The buffer is page size bytes in length. On x86, page size is 4096 bytes or 4K. The function should return the size in bytes of data actually written into buffer on success or negative error code on failure. The store method is invoked on write. It must read the size bytes from buffer into the variable represented by the attribute ATTR. The size of the buffer is always page size or smaller. The function should return the size in bytes of data read from buffer on success or negative error code on failure. Because this single set of functions must handle file I/O requests on all attributes, they typically need to maintain some sort of generic mapping to invoke a handler specific to each attribute. Okay, so creating new attributes. Generally, the default attributes provided by the k-type associated with the k-object are sufficient. Indeed, the purpose of a k-type is to provide common operations to k-objects. Sharing k-types between k-objects not only simplifies programming, but also provides code consolidation and a uniform look and feel to sysfs directories of related objects. Nonetheless, often some specific instance of a k-object is somehow special. It wants or even needs its own attributes, perhaps to provide data or functionality not shared by the more general k-type. To this end, the kernel provides the sysfs create file interface for adding new attributes on top of the default set. Sysfs create file. This function associates the attribute structure pointed by the ATTR with the k-object pointed at by k-obj. Before it is invoked, the given attribute should be filled out. This function returns 0 on success and a negative error code otherwise. Note that the sysfs opt specified in the k-object's k-type is invoked to handle this new attribute. The existing default show and store methods must be capable of handling the newly created attribute. In addition to creating actual files, it is possible to create symbolic links. Creating a symlink in sysfs is easy. Integrate sysfs create link. Okay. This function creates a link named name in the directory mapped from kobj to the directory mapped from target. This function returns 0 on success and negative error code otherwise. Okay. Destroying attributes. Removing an attribute is handled via sysfs remove file. Void sysfs remove file. So the function pointer that takes in 2 arguments. Okay. Upon call return, the given attribute no longer appears in the kobjects directory. Symbolic links created with sysfs create link can be removed with sysfs remove link. So sysfs remove link right here. Upon return, the symbolic link name in the directory map from kobject is removed. All four of these functions are declared in linux/kobject.h. The sysfs create file and sysfs remove file functions are defined in fs sysfs file.c. The sysfs create link and sysfs remove link functions are defined in fs sysfs symlink. Sysfs conventions. Wow, this is a lot of reading today. Keep going, we're almost there. The sysfs file system is currently the place for implementing functionality previously reserved for IOCTL calls on device nodes or the procfs file system. Instead of these deprecated kernel interfaces, today kernel developers implement such functionality as sysfs attributes in the appropriate directory. For example, instead of a new IOCTL on a device node, add a sysfs attribute in the driver's sysfs directory. Such an approach avoids the type unsafe use of obscure IOCTL arguments and the haphazard mess of /proc. To keep sysfs clean and intuitive, however, developers must follow certain conventions. First, sysfs attributes should export one value per file. Values should be text-based and mapped to simple C types. The goal is to avoid highly structured or highly messy representation of data we have today in /proc. Providing one value per file makes reading and writing trivial and from the command line and enables C programs to easily slurp the kernel's data from sysfs into their own variables. In situations in which the one value per file rule results in an inefficient representation of data, it is acceptable to place multiple values of the same type into one file. Delineate them as appropriate. A simple space probably makes most sense. Ultimately, think of sysfs attributes as mapping to individual kernel variables, as I usually do. And keep in mind ease of manipulation from user space, particularly from the shell. Second, organize data in sysfs in a clean hierarchy. Correctly parent kobjects so that they map intuitively into the sysfs tree. Okay. Associate attributes with the correct kobject and keep in mind that the kobject hierarchy exists not only in the kernel but also as an exported tree to user space. Keep the sysfs tree organized and hierarchical. Finally, remember that sysfs provides a kernel to user service and is thus a sort of user space ABI. User programs can rely on the existence, location, value, and behavior of sysfs directory and files. Changing existing files in any way is discouraged, and modifying the behavior of a given attribute, but keeping its name and location is surely begging for trouble. These simple conventions should enable sysfs to provide a rich and intuitive interface to user space. Use sysfs correctly, and user space developers can have a simple and clean, yet powerful and intuitive interface to the kernel. All right, the kernel events layer. The kernel events layer implements a kernel to user notification system on top of kobjects. That's cool. After the release of 2.6.0, it became clear that a mechanism for pushing events out of the kernel and into user space was needed, particularly for desktop systems that needed a more integrated and asynchronous system. The idea was to have the kernel push events up the stack. Hard drive full, processors overheating, partition mounted. Early revisions of the event layer came and went, and it was not long before the whole thing was tied intimately to kobjects and sysfs. The result, it turns out, is pretty neat. The kernel event layer models events as signals emitting from objects, specifically kobjects. Because kobjects map to sysfs paths, the source of each event is a sysfs path. If the event in question has to do with your first hard drive, sysblock_hda is the source address. Internally, inside the kernel, we model the event as originating from the backing kobject. Each event is given a verb or action string representing the signal. The strings are terms such as modified or unmounted that describe what happened. Finally, each event has an optional payload. Rather than pass an arbitrary string to user space that provides the payload, the kernel event layer represents payloads as sysfs attributes. Oops. Internally, the kernel events go from kernel space out to user space via netlink. Netlink is a high-speed multicast socket that transmits networking information. Using netlink means that obtaining kernel events from user space is as simple as blocking on a socket. The intention is for user space to implement a system daemon that listens on the socket, processes any read events, and transmits the event up the stack. One possible proposal for such user space daemon is to tie the events into dbus, which already implements a system-wide messaging bus. In this manner, the kernel can emit signals just as any other component in the system. To send events out to user space from your kernel code, use kobject uevent. Okay? With that struct pointer to a struct kobject passed in, sure, and then the action. Okay, so the first parameter specifies the kobject emitting the signal. The actual kernel event contains a sysfs path to which this kobject maps. Okay. The second parameter specifies the action or verb describing the signal. The actual kernel event contains a string that maps to the provided enum kobject action value. Rather than directly provide the string, the function uses an enumeration to encourage value reuse, provide type safety, and prevent typos and other mistakes. The enumerations are defined in linux/kobject.h and have the form of kobj foo. Current values include kobj move, kobj online, kobj offline, kobj add, kobj remove, and kobj change. These values map to the strings move, online, offline, add, remove, and change respectively. Adding new action values is acceptable as long as an existing value is insufficient. Using kobjects and attributes not only encourages events that fit nicely in a sysfs-based world, but also encourages the creation of new kobjects and attributes to represent objects and data not yet exposed through sysfs. This and related functions defined in lib/kobject uevent-c and declared in Linux kobject.h. Whew, finally. Okay. Conclusion. In this chapter, we looked at the kernel functionality used to implement device drivers and manage the device tree, including modules, kobjects, and the related ksets and k-types in sysfs. This functionality is important to device driver authors because it enables them to write modular advanced drivers. In the final 3 chapters, we switched the discussion from specific Linux kernel subsystems to general kernel issues, starting in the next chapter with the treatment on debugging the Linux kernel. Okay, that's going to be interesting. Yeah, I was wondering, because right now we've just been printing all the time. So we'll save that for next time. Thanks.